Yesterday we were introduced to our slope fields. And today we're going to look at some of those patterns. We know that if your derivatives equal to 0, you would have a horizontal tangent lines, right? We have to think in a slope field, all of those little tiny dashes are all little tiny horizontal, all tiny tangent lines. And if your derivative is 0, then you'd have a horizontal tangent line. If you have a vertical tangent line, that means that your slope is undefined. So dy dx does not exist. If your slope is positive, you have positive slopes. Well, I guess, okay, if your derivative is positive, you have positive slopes.
Sorry for the interruption, just a couple of things. One, the cafeteria will be closed this morning. It will still be open at lunchtime to purchase something with limited seating. And also, if you have a spare or during period change or break, you can get your beads from the front foyer for paper, rock, scissors, okay? Thank you.
You've already got some? Oh, this is so exciting. Paper, rock, scissors, beads. Okay. So positive slopes, derivative is positive because the derivative is just the tangent line slope. So that makes sense. Negative slopes, derivative is negative. If you have parallel dashes like in a column like that, that means they don't look quite parallel. And my attempt was to make them all perfectly parallel there. If you have a column of parallel dashes all the way through, that means your y-coordinate does not matter. And so your dy dx will not have a y. Similarly, if you have parallel slopes, everything in rows horizontally, that means your derivative doesn't have an x because the x-coordinate doesn't matter. I mean, some of these patterns seem kind of obvious, like periodic dashes means that your derivative is periodic. It's sort of like, okay. But you could see that like with the sine and the cosine curves, that your dashes will follow a pattern over and over again. And having this lets us figure out patterns and connecting slope fields to equations. All right, so here we have a slope field, dy dx is 2x. And we're going to use the slope field to draw the function. So you have it already there for you, but it gives you an initial condition that if x is 0, then y is negative 2. So the first thing you would do, and I have the whole thing on here, but the first thing you would do is put that dot on your graph, because you know that's part of your initial condition. And at that dot, you notice that the slope field was a horizontal line. So that's going to be either a maximum or a minimum. Then you think of all of those little tiny lines as being little tiny parts of your graph. So you just go towards, you're like, oh, there's my, you just sort of follow the slopes to draw your graph. And that's how you make an equation, a particular solution from your slope field. Now this is one, of course, you know. You could easily integrate 2x and get x squared plus c. And if you had an initial condition of 0, negative 2, that's the equation. It should be x squared minus 2. But it's nice to take equations that you know and see how drawing it within the slope field makes the shape quite nicely of what it should be. That looks like a parabola that I should have, right? Look at our graph. Just some things to check accuracy. I went through that point. What does that look like? not quite 1.5, right? What should it be? Well, if I was solving this, it should be square root of 2, which is 1.414. Does it look pretty accurate, actually? Worked out pretty nice. So it's just kind of interesting to see those kind of connections that a slope field, if you follow the slopes, can actually draw a really quite accurate graph of what your particular solution should be. Consider the differential equation dy dx equals xy over 2, and here's the slope field. And I've highlighted in yellow there the point 1, 1. Does it agree with the figure? Well, if you want to calculate dy dx at any point, you just plug in 1 for x, 1 for y, we would get a positive 1/2. Does that tiny little slope look like positive 1/2? Okay. Let f be the function that satisfies the given differential equation. Write an equation for the tangent line to the curve y equals f of x through the point 1, 1. Then use your tangent line to estimate the value of f of 1.2. So what we're doing right now is we're reviewing a topic that we did earlier. My question for you is, can you recognize the topic, or does this use the line to estimate the value of f of 1.2? Do you remember what we called that? I like the smiles, and someone went, no, right? This was called linear approximation. Do you remember our linear approximation? I say it now, but what's going to happen as we get closer and closer to the exam, you're going to do a bunch of review, and there are things that you learned, but you've kind of forgotten a little bit. So this is one of those linear approximation. What do we do with linear approximation? Well, we say that if you find the tangent line at a certain point, and you use that tangent line for something close, it's going to either be, if it was concave up, it would be a little bit of an underestimate. If it's concave down, a little bit of an overestimate. But if it's close enough, that tangent line will be quite accurate as an estimate. So first of all, we already know, we already know that our slope was 1/2, and we have our point 1, 1. So y equals mx plus b, or y minus y1 equals m times x minus x1. We can get that equation of our tangent line quite easily. You're probably pretty good at this already. Then if we want to estimate at 1.2, we just plug in 1.2 for x. And we solve this, and we would estimate the value to be 1.1. Now, if I took this point and I had that bothers me that I forgot an arrow. If I had that as my graph, this is saying that at 1.2, that green dot right there, does it look like it's at about 1.1? I'd say so. Pretty accurate. As far as using the actual slope field to estimate it as well. Okay, so here we use linear approximation to estimate. We could use the actual slope field too to look at that graph and estimate it as well. Question, could you find the particular solution in this one using the math that you know? Yeah, because the x and y are multiplied, you could separate the x and the y. So this is one that you could do with separation. And it would involve natural logs, because you'd have a 1 over y on the one side. So draw the solution of the curve going through -2, 0, and 0, 1. These are not the same solution. You're going to have two different solutions. So use one color for one, another color for the other. So we start by just labeling those points on that slope field and then following the curves afterwards. I'll put up the picture in a second, see if your picture looks similar to mine. That looks like a fun slope field. And you can try the next one as well on the next page. I'll put up this one, so if you're already getting ready for the next one, you can see. Did yours look similar? And what's interesting about slope fields is that green one and that blue one look totally different as far as graphs go. And that can sometimes be the case depending on your initial condition. Slope fields, I feel like, are calculus's version of advanced connect the dot pictures that you would have done in grade 1. Right? Sort of like, we've come full circle. I used to connect the dot when I was a kid and had so much fun. And I've been waiting for when I could reuse this in real life. And now those skills have come back with slope fields. Ooh, this reminds me of a wave crashing. I feel like I could start calculus therapy. Instead of those ink blots, I could just have slope fields and say, how does this one make you feel? Call it calculus therapy. What do you see? Do you see waves? Or do you see two sad faces? Oh. Sometimes when I think of creative things like that, I'm like, why has nobody ever thought of this before? And that's because it is not a good idea.
Do you have a deck of cards I can borrow from
I do.
you? Thank you.
Do you want one with all the cards?
Yes, please.
Okay.
Ideally. We have like a big thing in phys ed of like all these cards, but it's not like a deck, it's just random cards. So
There we go. There we go. That's
sorry to interrupt.
not a problem. I have lots, but I'm just making sure that I grab one that has. Oh, I'm feeling this one's gonna be good.
That looks pretty crispy.
Yeah.
It already looks better than what we got going, so thank you. Have a good day.
Identify the particular system that goes through a point. So the figure to the right shows the slope for the differential equation 1 minus xy. Sketch the graph that contains 0, 2. Label this as point A, and then sketch the graph that goes through -1, 2. That's graph B. And 1 minus xy. Can you separate the x and the y with multiplication? I don't think so. If you factor in a y, that 1 is a problem. So this one can't be solved by separation. And it might be one of the ones you can't get an equation for. And if you can't get an equation for it, then you're stuck saying, well, I'd have to use a slope field to figure out anything I want with this graph. But once you have the slope field, you could connect a certain point, you could draw a graph and you would have, even though you don't have the equation for it, you have the actual graph. So here we have our slope field. We plug in the point 0, 0, which is right there in the middle. There's no axes shown on this one. Do you see that you have vertical lines there? So you have a non-permissible value for your derivative. A non-permissible value seems to imply either you would have a corner on your original function, if it was continuous, or an asymptote. And in this case, it really looks like you have an asymptote. So based on the fact that you have a vertical asymptote, we're going to cancel out things here sort of systematically. We can cancel out C first because there's no vertical asymptote in y equals x plus 2. We can cancel out this one because tan has some non-permissible values. You can't do tan of pi over 2. You can't do tan of 3 pi over 2. And I don't see any more vertical asymptotes at those places. So I would cancel that one out as well. The first one, if you factor the bottom, has x plus 2 and x minus 2, which has two non-permissible values. And you would have another non-permissible value at 2, but 2 seems fine. So that one I'd cancel out. And as a result of canceling out 3, multiple choice strategy says circle D and be happy with it. Okay? This happened on the grade 12 provincial exam a number of years ago. That there was a multiple choice question where this was the strategy. And it made it through all of the major, like someone writes the test, someone makes a key, someone double checks the key, someone translates it to French, someone makes the key in French, someone double checks the key in French, and they missed the fact that everybody who did this question did this method of canceling out the ones that are for sure wrong, and therefore accepting that the last one must be right. But on the exam, the last one wasn't right either. It was just always the one you wouldn't cancel out. Because you'd always cancel out the other ones first. So on that exam, every single student got that question right because there was a mistake on the exam. So if we were going to be more thorough, we would then take this last answer and double check. Do things work out this way? Right? Do I get a horizontal slope at 0? Right? So if I took the derivative of this, is that one always going to be 0 when x is 0? So we could do some more work with this. Do we really feel like doing that today? No, but you could. Consider this differential equation. Hey, you could actually solve this one with separation and its slope field shown. Describe all the points in the plane where the derivative is -1. So here are all the points. I circled them here where the derivative is -1. Y can't equal 0 because, of course, then that derivative doesn't exist. And so just rearranging it, it is the line. Negative x minus 1. All the points on that line, except for where y is equal to 0, because it doesn't exist. And with that, we are officially done differential equations. And if you look, sort of in a way of being excited, applications of integration is our last calculus unit. And then there's the exam.